Now let's talk about how we actually measure water vapor in the atmosphere, the amount that we actually have there. So there are a few ways we can measure water vapor. One is what we call absolute humidity. This is the mass of the water vapor in a volume of air. So the units are in kilograms or grams per cubic meter, mass per volume. We also have what's called the specific humidity, which is the mass of the water vapor, what we also call the mixing ratio, relative to the mass of the air in total. So this is mass per unit mass, so it actually doesn't have any units, grams per kilograms. And then the one you hear about a lot on the news is what we call relative humidity, and this is given in a percentage. This is actually the specific humidity, so the actual grams of water vapor per kilogram, relative to the saturation specific humidity. And saturation means what's the maximum water vapor we could actually put into the air. And we'll talk about how much we can put into the air in a few seconds. So relative humidity is a percentage of what the maximum could be. And this is what you use on the news when people are saying it's going to be 60% relative humidity, 80% tomorrow. It's relative to saturation, where saturation means that basically a cloud will start to form. Another way of looking at the relative humidity is the actual vapor density in the air compared with what we could put, the saturation vapor density, how much we could put into the air before it gets saturated, and multiply this by 100 to get it in percentage. How do we get relative humidity of 100% so we get to the saturation? Well, let's look at this little experiment here. If we have this container on the left, water with a flat cover on top of it so that the water cannot evaporate. So the air above the water, above this surface, is completely dry. As soon as we take off this lid off the water surface, some of the water molecules are going to start leaving the surface of the water. They're going to evaporate. But some will also return back to the water surface. But you can see by the size of the arrow, initially there's going to be more evaporation than condensation of the molecules going back onto the water surface. But if we wait long enough, we'll reach equilibrium. We're going to have the same amount of molecules leaving the water surface as returning to the surface. And then the amount of water that we have is the saturation vapor pressure. This is how much we can put in at the maximum into this volume above the water. And this determines what we call relative humidity of 100%. And this is where the evaporation equals the condensation in the air. So if we have an atmosphere outside where the relative humidity, like they say on the news, is 100%, and you put a cup of water on your desk, eventually it'll evaporate and disappear, all that water. But if it's above 100%, then we're going to have condensation. And this means that when we reach 100% relative humidity, we're going to start to see droplets condensing. And in other words, this means clouds are going to start forming in the atmosphere. So when you look up outside, when you go outside or look outside the window and you see a cloud, inside that cloud, there has to be relative humidity of at least 100% for there to be droplets there. The clouds are made up of droplets of water, and they're only there because the relative humidity is 100%. The air is saturated there with water vapor. Now this curve is quite a famous curve called the Clausius-Clapeyron relationship or curve. And this shows how much water vapor we can actually put, the maximum amount of water vapor we can put into a volume of air as a function of temperature. So the y-axis is the specific humidity, grams per kilogram. The x-axis is temperature. And the line we see in the middle shows the line of 100% relative humidity. It's also a line we call the dew point temperature, because this is when dew will form, when we get to that temperature with that amount of water vapor in the atmosphere. And the further we are away on the right-hand side of that curve, the drier the air will be. So there are three ways actually we can reach saturation, we can reach a relative humidity of 100%, or we can produce a cloud. The first is that we can simply cool the air. We can go from A to B to C. A, we have no cloud, no saturation. As we cool the air, we go towards B. At B, we'll start to see a cloud forming. And if we cool the air even more towards C, the cloud will just get more thicker and thicker, and there will be more and more droplets growing in the cloud. Another way to grow and produce a cloud is to just add water vapor. So we can go from E, D, C. At the point E, we have no cloud. we're underneath the line, so we're not saturated, maybe relative humidity of 60%. If we add more moisture now, we'll eventually get to D, and then we'll be saturated and we'll start to see droplets form. And if we move further, we put more and more moisture, we go up to C, again the cloud will simply grow and we'll get larger droplets. And the third way, which is actually what happens in nature, is to take two masses of air from different regions and mix them together. So we can take one mass of air, this one down here, which is basically very cold air, so it's around 0 degrees, and very dry air, so it's only got maybe 4 or 3 grams per kilogram. And we can take very moist air, say from the tropics, which is warm air and it's got lots of moisture, and we take cold air from Europe or from the Arctic. We bring them together over the Mediterranean, we mix them together, and we're left with this point here, which is above the line of the Clausius-Clapeyron relationship. So just by mixing two different air masses together, we can get saturation and clouds can form in the atmosphere. So, as I mentioned, let's look at this in more detail. Firstly, how can we reach saturation in the atmosphere? The first way is by simply adding more water vapor. So let's look at this yellow line here we have on the plot. If we start here in these boxes, in the green boxes, and we keep the temperature constant. So for every box, the temperature is 25 degrees. But we add more and more water vapor each time. So we start out, first of all, with 5 grams of water per kilogram of air. And we'd see that if we take 5 over 20, we have 25% relative humidity. 20 is the maximum we can have. If we then double this to 10 grams, 10 grams out of 20 is 50% relative humidity. And now we add more water vapor, we double that again to 20 grams, 20 out of 20 is 1 or 100%. So by simply adding water vapor, we can reach saturation. So by knowing what the temperature is and knowing how much water vapor, we can calculate what the relative humidity is in the air. And examples of this are if you go out on a cold winter morning, it's cold outside, so we don't need to add too much water vapor before it condenses and reaches 100% relative humidity. From our mouths, we have lots of water vapor coming out. On a warm day, that water vapor will not reach saturation, so we won't see the droplets. But in these pictures, on a cold day, we don't need a lot of water vapor in order to cross that line of the Clausius-Clapeyron. And this is what you actually see here are droplets being formed in the atmosphere. These are very small clouds coming out of our mouths because the water vapor is condensing and reaching 100% relative humidity. Another example are planes which fly up high where it's really cold. And so, again, you don't need too much water vapor for this to condense. What we call contrails. Contrails are condensation trails from planes. These are actually ice crystals. It's so cold up there that we don't have droplets forming. We have ice crystals forming. And it's the same way we're adding lots of water vapor from the exhausts of the plane to the atmosphere. It's very cold, so immediately these condense into ice crystals. The other way that we can actually reach saturation and produce a cloud, which is often more common than adding more water vapor, is to simply cool the air. So now let's look at this yellow line again. And now we have a constant amount of water vapor. So now the water vapor is about 3.5 grams per kilogram. That's this horizontal yellow line. And now we're going to cool the air from 20 degrees to 10 degrees and to 0 degrees. And what we see is that initially at 20 degrees, we could actually have 14. Maximum is the 14 we could have before saturation. So it's 3.5 out of 14 is 25% relative humidity. At 10 degrees, the maximum we can have is 7 grams per kilogram. 3.5 out of 7 is 50% relative humidity. And when we cool it down to 0 degrees, we've reached the maximum. 3.5 out of 3.5, we've reached 100% relative humidity. So here, by cooling the air, but not changing the amount of water vapor, we can produce a cloud. And this is what often happens when we have air rising in the air. We take the water vapor from the surface, which is not saturated. We rise it up, cools, and eventually it will reach saturation and a cloud will form. An example of this is simply fog. Fog which forms in the nighttime. We have, again, going from A to B to C. On the top left plot, we're taking air which is not saturated in the daytime. At nighttime, the temperatures drop, it starts to cool, gets to B, and as you can see on the bottom left around the forests, we start to see fog. Sunrise in the next morning will warm up that air and we'll go back from B back to A, and the clouds will disappear, the fog will evaporate because the temperatures are rising. So fog, which we see during the nighttime close to the ground, is caused exactly by this process where we're cooling down the air until we reach 100% relative humidity or the dew point temperature, and then we have condensation of droplets and we see the fog or we see clouds. So by cooling the temperature, we can result in condensation and produce these clouds. Now, to measure actually the dew point temperature, you can do an experiment by yourselves at home. Take a glass of water, put a thermometer in it. The thermometer will show the air temperature in the room. Now you can take some ice and put it into the water, and you'll watch the thermometer go down because the ice is cooling the water. And eventually, at a certain temperature, you'll also start to see the little droplets forming on the outside of the glass. Where are these droplets coming from? This is the moisture in the air which is touching the glass, which now, because the temperature has reached that dew point temperature, you start to get the little drops of dew forming around the glass. And that will give you exactly what the dew point temperature is. Again, this depends on how much moisture you have in the air. The drier the region, the lower the temperature will go relative to the temperature outside, the starting temperature. If it's a very humid atmosphere, the difference will be much smaller between the temperature of the water in the beginning and the temperature at the end. I hope you'll think about this next time you have a beer and you look at the droplets around the beer and talk about the dew point temperature. And if you're in a very, again, moist area, it doesn't take a lot to cool your beer and to get the drops around the side. If you go to a desert region, you have to cool it a lot more before you see the droplets on the outside. And we see this also during the day and night, the diurnal cycle of the temperatures. We know that after sunset, the temperatures start to cool down, reach the minimum temperature during the day around about 6 a.m., just before sunrise, and then things start to warm up again. And maybe the maximum temperature 2, 3 in the afternoon. And then again, as the sun starts to set, we start to see the cooling. If the temperature drops below the dew point temperature, shown in green here, TD, during the nighttime, then we'll start to see dew forming on the plants at the ground. Because like the fog, the water in the air around the leaves is becoming saturated, and we can have droplets forming, water droplets on the grass. And if that temperature is actually below zero, then instead of water droplets, we'll get ice crystals forming on the plant, and that's what we call frost. And because of this relationship of Clausius-Clapeyron, if we look on the little blue plot, going from, again, A to B to C and back to A, there's a relationship between the relative humidity in the air and the temperature of the air, and they're inversely related. The warmer it is, the lower the relative humidity, because the warmer it is, the further away we're going from the line. We're going to warmer temperatures, lower relative humidities. We can see here in the plot, the blue curve, when we have very low temperatures, say at 6 in the morning before sunrise, that's when we have the dew. That's when we have the highest relative humidity, and often we get to 100% and we see dew on the grass. In the late afternoon, 2, 3 in the afternoon, we have the highest temperatures, which means we're further away from the curve of the Clausius-Clapeyron, and we have the lowest relative humidities. So we have this opposite relationship between temperature and relative humidity if the actual amount of humidity remains constant over this day.